Let me begin by thanking Mikkel and the other organizers for what is proving to be a wonderful meeting. It's always amazing to see the staggering progress in this field, how rapidly things are evolving. So I've gone for the non-controversial title of Full Quantum Control of Ultracold Polar Molecules. Right. So in terms of motivation, I'm not going to spend very long, but because we've heard a lot of talks already. But of course, what attracts many people to molecules is this rich internal structure of rotation, in which we can encode spins or qubits, coupled with the existence of long-range dipole-dipole interactions, which one could then use to entangle these spins. In particular, if we can get complete control of the molecules and place them in optical lattices or optical tweezers, then we have this wonderful platform in which to explore these rich and varied proposals in the areas of quantum simulation and also quantum computation. And we've already learned how this is also a platform for engineering squeezing, and I think ultimately these kind of experiments may feed into the precision measurements with molecules, where we could dream about having entangled samples for those precision measurements. We've also come across this challenge, right? These applications actually require us to be able to engineer coherence times in the molecule, which are going to be considerably longer, ideally much, much longer than the dipolar interaction timescale. And so here's some numbers on this for rubidium cesium. If we were able to produce it in a perfectly filled optical lattice, then the nearest neighbor interaction would be around 1 kilohertz or so. Alternatively, if we put the molecules into optical tweezers 2 microns apart, then this interaction becomes around 20 hertz. So this 1 to 50 millisecond timescale is the strong dipole-dipole interaction that attracts us to these systems. Okay. We've also learned already today the problems of optically trapping the molecules that comes from these anisotropic polarizabilities, which generally leads to very rapid dephasing. And this is some old results from our lab. And this plot is difficult to see, but the timescale here is millisecond, and so the coherence time we were achieving in this experiment is of order 1 millisecond at best. Okay? So we're certainly not satisfying this requirement. And this actually makes the observation of dipole-dipole interactions in molecular systems very challenging, which is why there's only been a few experiments that have demonstrated this. And just to reiterate, I mean, this is a collection of beautiful results from many beautiful papers, but typically these timescales for coherences in optical traps with molecules is on the order of milliseconds. And there have been many tricks to try and enhance that, such as the magic angle tweezers, using near magic lattices, and Gabrielle told us about the magic ellipticity tweezer. And so everybody's striving to find a solution to this common problem. So what I'm going to talk about today is, I'm going to try and address both sides of this inequality. Okay, so first of all, I'm going to tell you how I think we know now how to eliminate this problem. And in our case, that's by constructing a magic wavelength trap for rotational states of the molecule. And then I'm going to tell you about some experiments that we've just begun where we're going to work on the other side and try and increase the interaction strength, okay, by introducing Rydberg atoms into the system. So let me quickly reiterate the problem of the anisotropic polarizability. Essentially, it comes down to the fact that the polarizability of even a simple diatomic molecule is different, orthogonal to the bond axis and parallel to the bond axis, which leads to this polarizability that has an isotropic term, which is good. It contributes to trapping and is the same for all rotational states. But then there's also this anisotropic term, which basically depends upon the difference between these two molecule frame polarizabilities. Okay. This is almost zero in the rotational ground state. And in fact, my group and other groups have demonstrated that in terms of hyperfine state coherences in the ground state of the molecule, the rotational ground state, it's possible to achieve coherence times of many seconds. And we'd like to extend that to rotational states, because being in the rotationally excited states gives us access to these dipole-dipole interactions. The problem is when we move up to higher rotational states, this interaction actually mixes different MF, or different MN projections. And you can see that just in the MN basis, but if you write out the matrix elements of this anisotropic polarizability, you have diagonal terms, but also these off-diagonal terms that are going to mix the states. And all of this scales, just to reiterate, of course, with this parameter, which is going to be important, alpha 2. So this becomes more complicated in the presence of molecular hyperfine structure in a case like rubidium cesium, because that also mixes the MN states. And this is what it looks like. I'm not going to go through this in detail, but what we're looking at here is the transition frequency from n equals 0 to n equals 1 in the molecule, starting from the lowest energy state and driving up to different hyperfine states, and how those states vary as a function of intensity. And this depends also on the polarization of the laser, trapping laser, with respect to the quantization axis. So the message here is generally you get very strong intensity dependence to these rotational transition frequencies in an optical trap. And of course, when your molecules are in a gas and sampling different places in the trap, this leads to rapid dephasing. And it's all due to this anisotropic polarizability. So how are we going to get rid of this? Well, we're going to tune this alpha 2 to be 0. Okay? And the way we're going to do that is we're going to recognize the fact that the alpha parallel and alpha perp actually come from different sets of transitions within the molecule. Okay? So then the solution should actually spring out to you that if you set your laser frequency to be close to a particular transition, then you can tune one of these components without really affecting the other. Okay? And that's exactly what we're going to do, and we're going to go to this X to B transition in the molecule. It's around 1146 nanometers in the case of rubidium cesium. This is nominally forbidden, but there's some weak mixing with this singlet sigma state, and that allows us to tune alpha parallel in the vicinity of this wavelength without affecting alpha perp. Okay? So the idea is you tune alpha parallel to be exactly equal to the background value of alpha perp, and this anisotropic polarizability problem completely vanishes. Okay. So this is what it looks like. We're going to park the laser frequency between the vibrational levels, the two lowest vibrational levels of this B triple pi potential. And then this is what the polarizabilities look like as a function of detuning here. Okay, so we get these poles whenever we hit a transition. Okay. So this is the V equals 0 pole, and then the V equals 1 pole. Alpha parallel tunes nicely, and alpha perp is unaffected. Okay, so if we tune to this particular wavelength, they become identical, and alpha 2 vanishes. And we can see that if we compute the polarizabilities of the ground state of the molecule and the first rotationally excited state, then they cross at this magic wavelength, which is around 180 or so gigahertz detuned from this transition. Okay, you might be panicking and saying, oh, but tuned close to a transition, that's generally bad, right, because of photon scattering. But actually, because these are normally forbidden and there's only very weak mixing, the line widths of these transitions are on the order of 10 kilohertz or less. So we're actually far detuned in terms of line widths. So we can measure this. So here we're measuring the light shift of the 0 to 1 transition in the molecule as a function of the laser tuning. This is the free space value, and you can see poles just exactly as predicted whenever we hit a transition in the excited state, to the excited state, and associated with each one of these is a magic wavelength, a rotationally magic wavelength. We can zoom in on one of these and do a more precise spectroscopy measurement, and this is a very complicated plot. But basically, the different colors here are all different transitions within the molecule. Okay, so green and red, for example, are n equals 0 to n equals 1, different hyperfine states. Blue is 1 to 2, yellow is 2 to 3. The solid dashed lines are different polarizations, and the key point is they're all intersecting at this same detuning of the laser, indicative of the fact that we're tuning alpha to be 0 in this case. So actually, we get magic frequencies from many rotational state combinations, all within a gigahertz or so. To set these magic wavelengths more precisely, we actually do a Ramsey measurement. And so we can do this in the presence of the trapping light and look at how the contrast of these Ramsey fringes varies as we detune away from the nominally magic frequency. And you can see these fringes varying. And we plot those out. So here we're plotting that fringe contrast as a function of the laser detuning. And we've done that here for a whole variety of different rotational state transitions within the molecule, for reasons which will become evident. And you see that they are all within this 1 gigahertz or so window, as we talked about. Okay. In particular, I'm going to look first at this combination. So this is a transition from n equals 0 to n equals 2 in the molecule. It's a 2-photon transition to create that superposition, and then we see we can enhance the coherence by sitting at a very particular wavelength. So this is what we then measure when we vary the Ramsey time, the evolution time between the 2 pi by 2 pulses in the system, okay, for this particular superposition. And we've chosen this because there's no directly allowed transition dipole moment between these states, and so there's no dipole-dipole interaction in this gas of molecules. Okay? And already we see we can get coherence times of almost a second, just bare coherence times now. And this is completely limited by how well we've set the laser frequency. The way we're locking the magic wavelength laser is not very good presently, and that's what's limiting the coherence here. With a simple spin echo, actually we see no loss of coherence over the measurement time, just a simple pi pulse. So this is 1,000 times better than we've ever done before, and so we were really excited about this. And what we're particularly excited about is this second scale coherence is now long enough to see dipole-dipole interactions in this system. And to do that, we go to a different superposition. Okay, so we go to a superposition of 0 and 1, and this creates a rotating dipole in the molecule. So now we have a gas of rotating dipoles that are going to interact. Okay? And that limits the coherence time to around 157 milliseconds in this case. And this is just dephasing due to this random distribution of molecules and dipoles. Okay? So for once, the dephasing is really good here, right? Because having worked on molecules for 10 years, this is the first evidence of seeing a dipole-dipole interaction for us. And we worked with Caden and his group, and they simulated this, and the timescales agree, so that's encouraging. The other thing we can do is change the dipole interaction strength by using different combinations within the molecule. So that's what these other state combinations do. They result in different oscillating dipoles with different strengths, and then we can measure the coherence time as a function of these, the dipolar strength, and that fits exactly as you would expect to the scaling for the dipole-dipole interaction. Okay. So we believe with this we've engineered second scale coherences in rotational states of the molecule, and really now have access to dipole-dipole interactions in this same case. I should say we have a very dilute gas of rubidium cesium molecules. The actual dipolar interaction strength is about 2 hertz, 2 or 3 hertz, and so we're able to detect the presence of that because of this magic wavelength. Okay, so time is ticking on. So let me now switch tack completely and tell you about a different experiment where we want to reduce the interaction time by adding a Rydberg atom to our experiment and enhancing the interaction between molecules. We've seen this slide before, okay, and we know we're all convinced that polar molecules are the best dipolar system, but we have to acknowledge there are others out there, not least the highly magnetic atoms and Rydberg atoms, and you could look slightly enviously at some features of the Rydberg physics, right? Not least these killer Debye transition dipole moments that they have access to. So the motivation for this is, to construct a hybrid system where hopefully we can harness the best of both worlds, both polar molecules and Rydberg atoms, and throw away all the problems. That's the dream. And actually, when you look into this, there's a whole host of proposals to combine Rydberg atoms and molecules. Several papers have discussed using Rydberg-mediated interactions to entangle molecules. The problem that we're really interested in is using the Rydberg atom to non-destructively read out the presence of a molecule, even the state of the molecule. There's new physics in combining Rydberg atoms and molecules in the form of these giant polyatomic Rydberg molecules that have been predicted. And there are exotic methods of cooling molecules with using Rydberg atoms have been studied. Okay? So how we're going to do this, we're going to take the tweezer approach. And here I'm going to acknowledge we were greatly inspired by the experiments that Gabriel talked about earlier today in Kangwen's lab. So I'm not going to talk you through about the way we make molecules in tweezers. Just to say that the key thing is a lot of what we do in this is always very destructive, the imaging. Okay, so having formed a molecule following the route that Gabriel described, just as he does, we always reverse the STIRAP, reverse the magnetoassociation, unmerge the atoms. It's ultimately super destructive measurement of the molecule. The experiment looks very similar to what Gabriel presented. So it's a high NA lens focusing various different wavelengths into a glass cell where we can trap and detect single rubidium and cesium atoms with very high fidelity. When you start one of these experiments, you always write some pattern in atoms, and it's actually obligatory to draw your local landmark. So if you've not visited the Northeast, this is the Angel of the North, whose wingspan is about 50 meters, I think. Here it is in cesium atoms, about 50 microns across. We do the same Raman sideband cooling, so we have to put the atoms in the ground state of the tweezers. This is a fairly established technique now, and we get high occupancy in the motional ground state for both rubidium and cesium. We then do this very careful merging of the potentials to bring the two atoms into the same optical tweezer in order to then make the molecule. And after this, we estimate that we have about 60% of the atom pairs in the ground state of relative motion in the correct hyperfine state to make the molecule. Actually, in doing this, we accidentally discovered a new method for forming molecules in this paper, and Jeremy's going to talk about that next. So I won't say any more on that. So this is typically what we have in the experiment at the moment. We load of order 10 tweezers of rubidium cesium. We can do rearrangement on those. And then we magnetoassociate, typically with 4 doubly occupied tweezers or so. And we produce a molecule in around 50% of the time where we had an atom pair. STIRAP is very efficient. It's 96% in this case, and we can measure that by just repeatedly going back and forth to the ground state. And that's the data here. Very quickly, we can take everything we've learned in the bulk gases and just switch it over to the tweezers, so we can do microwave transitions very cleanly. This is going up to n equals 3 in the case of the rubidium cesium. We've actually gone up to n equals 6. So we can access this nice ladder of internal states. And of course, I set the title of full quantum control. So you can also do single site addressing. Okay, so here we've applied an additional laser to stark shift some tweezers, and then you see a shift in this microwave transition frequency, which allows you to then drive pi transitions on one site and not the other. And this is just the data showing, having done a pi transition on half of the sites, we can drive Rabi oscillations out of phase. Okay, so we can prepare a spin up, spin down type system very easily here. Just as Gabrielle said, we can also do the multi-stage readout. In our case, we do it slightly differently. What we do, rather than imaging at high field, we post-select. So we STIRAP back and then pull out a rubidium atom and then apply a microwave pulse to transfer the n=1 population back to n=0, and then do a second STIRAP and pull out the rubidium atom again, and we end up with 2 detection tweezers. And so if the atom is in here, then the molecule is in n=1, but if it's in this box, then it was in n=1. So in that way we can do multi-state readout. And I think pulling out separate tweezers, we could in principle extend this to more rotation states. Okay, but what I really want to get onto is to tell you about the experiments we've been doing in this collaboration with these wonderful people to look at combining a Rydberg atom and a polar molecule. And what they've calculated for us is to show that actually if we could position a Rydberg atom within around 300 nanometers or so of a polar molecule, then this charged dipole interaction in which the electric field from the Rydberg atom actually polarizes the molecule leads to this pair state energy shift of order tens of megahertz or so. Okay? But of course the challenge is getting your atom and molecule within 300 nanometers of one another. So we do that actually using state-dependent potentials. Okay, so we use 1065 for the molecule and 817 for the rubidium atom, which actually almost has no effect on the molecule. And when we do this, we can actually bring the 2 tweezers to within 400 nanometers of one another. And then the atom-molecule separation, because of a slight crosstalk, goes down to around 310 nanometers. And we can get this close. You can see that the wave functions, because both the atom and the molecule are predominantly in the motional ground state of these tweezers, the wave functions are not overlapping, and so we see no loss, even at this 300 nanometer distance. So having positioned them there, we then apply, we excite the rubidium atom up to in this case, the 52s Rydberg state with a 2-photon scheme, and we leave the trap on, and the trap is repulsive for the Rydberg atom, and so the Rydberg atom is rapidly kicked out, and that maps Rydberg excitation onto atom loss. And so we can then see the effect of the molecule. So here in the detection tweezers, we only have an atom, and this is the atom survival probability as a function of the pulse duration of this Rydberg transition. And so here we promote the atom up to the Rydberg state and then back, and we see the usual Rabi oscillations. Okay, and we fully understand this. The dephasing is just due to the frequency noise on the lasers that we have. We then do the same thing, but now we have a molecule present in this tweezer, which is 300 nanometers away, and we see strong suppression of this Rydberg excitation. So this is the blockade of the Rydberg transition due to the presence of a polar molecule, due to this charged dipole interaction. Okay. So already this gives us a not very good fidelity, but a way of measuring the presence of the molecule without actually destroying it. Okay. So this is a route to non-destructive detection of the molecule. We can also do the spectroscopy. So this is at a massive 700 nanometer separation. And of course, there's no difference whether the molecule is present or not, because this charged dipole interaction is effectively 0 at this distance. But at the 300 nanometer, again, we get exactly the same spectrum for atom-only case, but now this is smeared out and lost when we have the molecule present. As an outlook, we're greedy, we want to go even stronger, and the way to make this interaction even stronger is to engineer a resonant dipolar interaction. And so this is from Mike's paper recently, and there was a similar paper from Kang-Kwen Ni's group, and the idea is you pick a pair of Rydberg states with an electric dipole allowed transition whose frequency exactly matches a rotational splitting in the molecule. And then you get a resonant dipole-dipole interaction, and it should be possible to get megahertz type interactions at 1 micron scale separation. Okay. And this is just to show calculations for rubidium and for cesium. So these dashed lines are all the rotational transitions in the molecule, and these are all the different Rydberg transitions, and basically there are many, many possibilities. What we're targeting in the lab at the moment is this combination, and we hope to see this nice hopping of the dipole between the Rydberg atom and the molecule. Okay, my time is definitely up. So what I hope I've maybe convinced you that in elements we have this full quantum control now of the molecule. Now have really long rotational coherence times as well as nuclear spin coherence times. And the next step there is to put these molecules into optical lattices of the type that Carl talked about earlier. And the tweezers is just a wonderful platform to play around with. Here we really have single site addressing and control of the molecules. They're prepared in the motional ground state of the tweezer predominantly, and there are many possibilities for enhancing interactions there. I have to acknowledge that the team that do this, in particular, Phil Gregory and Alex Guttridge, are postdocs who lead these two experiments, and just like everybody else, we're looking for more people to come and join this activity. So let me end there, and thank you for your patience as I overrun.
Thank you very much for a great talk. Other questions?
Thank you. Just like near the beginning of your talk, when you were talking about the zeroing the tensor polarizability, and then you had a plot where it was like peaking, the contrast was peaking or something as a function of the wavelength of your magic wavelength light, but it seemed like there was different peaks for different transitions.
Yes.
I was thinking if the tensor polarizability was zero, wouldn't they have been the same?
Are you talking about?
Oh, sorry, I should have remembered the number.
This?
Yes, that was, yeah.
Yeah.
My misunderstanding.
No, you're right. Actually, it's not absolutely perfect in terms of actually, if you look into the theory, there's a small residual interaction in the anisotropic polarizability, which is actually what's also leading to this slightly different frequency for all the different rotational combinations.
Why? Like if you've tuned it, like there's only two things. Can you not tune them to zero?
So no, we are tuning the to zero.
Yeah.
But the fact that they don't all coincide is because there's a residual bit which we also have to compensate. So if it was straightforward to just let me have a maybe this helps. So this is the theory, and basically this bottom line, if that was all there was without this Tn term, then all of those rotational transitions would be exactly have the same magic wavelength. But this Tn term, which is a little residual bit, shifts them around. We still compensate the Tn term for each individual one, but that's what leading to the slightly different wavelengths. Okay. So this Tn term is the one that, well, the bit left over, and that's its form, and it kind of has all of the rotational structure in it. Okay, and so it turns out in rubidium cesium, it's very, very small, but it's detectable. Okay, so that's why those peaks don't all line up exactly. No, I mean, I think that's the problem, right? So it depends on the rotational structure, the line widths, and so on. So it's all slightly different. Rubidium cesium is very nice because this detuning is, actually this is an old slide, is out at 185 gigahertz. Other molecules, it's much closer. Actually, some molecules, this intermediate magic wavelength between the vibrational poles doesn't even exist. Yeah.
Okay, thank you. And then I guess we move the remaining discussion to the poster session, or at least after the session. Thank you again for your talk.